So, the construction, in fact, even the existence that we are interested in of a super concentrator, it should be a graph family. So, n tends to infinity, and for growing n you want the vertices and the edges, both of them, to be order n, right. And remember that there should be this very strong connectivity property via disjoint paths. So, we will give this construction by probabilistic methods, and we will define first a weaker object, just a concentrator. So, N1, N2 U concentrator okay, this is a bipartite graph. That has N1 input nodes, let us call them I as before, N2 output nodes, let us call them O, such that for all k up to u, so you can think of u subsets of I and u vertices of I and that of O. So, for all s I u or I k, sorry, k vertices, and similarly k vertices of O. Again the same thing, vertices in S connect to T by k disjoint paths. And the key thing here is that the quantifier will be flipped. So, it is not for all, this is there exist. So, this is the only change in concentrator. So, up to this bound u, upper bound u, you can take k vertices, call them S, and for those k vertices there is some subset T such that S to T there are disjoint connections, disjoint paths. Okay. So, obviously, this there exist is much weaker than for all. So, for every S there is a different T possibly, and other T's may not work, right. So, this is a weaker notion. We will first construct this. First we show this lemma that concentrators do exist and very few edges, with very few edges and vertices. So, an efficient randomized algorithm constructs a 6J, 4J, 3J concentrator of size linear in J. Okay. So, this I union O, the vertices, that is only 10J, and the number of edges will also be some constant times J, right. So, this is really what we want for super concentrators, but this here is a first algorithm to actually construct concentrators. then we'll use that to construct superconcentrator. Okay, so not only do concentrators exist, we'll actually optimally find them. So let's do that. Let's do the construction, and it will also be an algorithm, randomized polynomial time algorithm. So consider a bipartite graph G, which is I disjoint union O. So vertices are partitioned into input and output nodes, and then there are edges across I O. With I6j and O4j. Let E be randomly chosen 36j edges. Okay, so think of this as a larger I and a smaller O, and then the edges are like this. Okay, so the edges are only across. There are no edges inside I or inside O because we want a bipartite graph. So of course, between 6j and 4j, there could have been 24j square edges, but we'll make do with 36j only. Okay, so pick them in a random way. Place them as so these are the conditions, special conditions. So out degree of each U in I is 6, and in degree of each V in O is 9. Okay, so if you look at the edges out of I, so number of out edges of I is I times 6 and number of in edges of O is 9 Cartesian product O, right, and both these are, as you can see, 36j. So we will think of the representation of this graph G. Representation of this graph G we'll think of as adjacency list representation, where the neighbors are in order. Okay, so it's an ordered adjacency list. So we can first look at the vertices in I and place the 36j edges, and the same thing we can do symmetrically on O. So what you get is any bijection from the I side to the O side it defines the graph with an ordered adjacency list. Okay, so that's the one-to-one correspondence between the graph and the bijections. So one-to-one correspondence is given this way. Now, how many bijections are there? That is just like permutations, right? So 36j factorial. So number of such g is 36j factorial. So out of these, now we have to see whether there is a concentrator. How do we check that? So for that, we have to see whether vertices up to 3j on the left and on the right, on the left if we choose, then whether there are disjoint paths to some t in O, right? So we have to check that. So let us instead count the number of non-concentrators. So let's do that. So if G is a non-concentrator, then there will be an S which will not have a T, right? So then there exists an S in I such that for all T on the right hand side, what happens? Something bad happens, right? This disjoint path connection is not there. S is not connected to T by disjoint path. And there exists a K smaller than 3j. Right. So for there is an S which is bad, which means for all T, disjoint path connection is not there. So from this, what you can deduce is that the neighborhood of S this size is less than K. Okay, this is by something called Hall's theorem. So read about this. This is a theorem about bipartite graphs especially. So it basically says that if for all S the neighborhood was at least K in size, then there would have been a matching. Okay, so then the above thing would not have happened. So since it's happening, then it means that there is an S which has actually even the neighborhood is small. And let me put here that in fact there is an S with small neighborhood. Okay, it may not be the same S as before, but there will be an S of size, some size, such that the neighbors are fewer than itself. So now let us use this S. Say of size K to count. So what will we count? We will count the number of non-concentrators. So basically, as you are picking these random edges, what is the chance that you hit a non-concentrator? Is the probability 1? So we'll actually show that the probability is not 1. So let's do that to count non-concentrators. Okay, so first thing, the way we read this orange statement is that neighborhood of S is a proper subset of some k-sized T. So NS is a proper subset of some k set on the RHS, which means that these 6k out edges of S right, they are matched with less than equal to 9k in edges of T. Right. So look at S, the edges which go out of S, they are 6k many, and they are all going inside a T which is of size less than k, and the number of in edges to them is less than equal to 9k. I can even put less than 9k here, and so these two have been matched, right, in our the way we are building this graph, right, the bijection that we had before, the one-to-one correspondence between the edges and the permutations. So basically the 6k are being matched by these very specific 9k, and this already will be enough to give you the result if you do the count carefully. So let's do that. All these are will give you non-concentrators, right? So let's do that calculation. So this implies that number of non-concentrators for this S and T is less than equal to, so other than these 6k there is no condition, right? So 36j minus 6k you can permute as you wish. Only for this 6k you have to map them to the 9k ones. So that is how many options? So out of 9k choose 6k and then you can permute them. So 6k factorial. It just this very lazy count actually get strictly smaller than. So which means that number of non-concentrators now you vary k, S and T. So if you vary that, then what do you get? Then you have to sum up the above value. So that is k equal to 0 to 3j, because k can go a maximum to 3j. And for that, how many S and T? 6j choose k times 4j choose k, right, times 9k choose 6k, then 6k factorial, and 36j minus 6k factorial. That's the number of non-concentrators, upper bound. So which means that the probability of hitting a non-concentrator, that G is non-concentrator, it is less than the above thing divided by 36j factorial, right? So you get sum of all these k's, 6j choose k, 4j choose k, and 9k choose 6k divided by 36j factorial, and with these remaining terms you actually get 36j choose 6k. So that's the probability, and with some effort basically look at the value k equal to 0 and the end value k equal to 3j, and from that you can deduce the way this function grows. You can deduce that the sum is actually small. This is actually smaller than each of these summands. In fact, they are smaller than 1 over j to the 4. So it is in particular less than 1. Okay, so the probability of hitting a non-concentrator in this process is actually not 1, which means that there is a concentrator. So this means that a 6j, 4j, 3j concentrator will be found with high probability and it will have edges, as we used only 36j. So this probability or simply counting proof does give you concentrator as promised. Now from concentrator, how do we go to super concentrator? That's one more step. So that will be theorem 6. So a randomized polytime algo designs a super concentrator G vertices V edges E with number of vertices 20j and number of edges, some multiple of j, order j definitely. So this actually you can now use concentrator to build this. This is not very hard. Once you have a concentrator, you can use 2 concentrators to get to this. So this is how we'll build it. So use the lemma to design the following network. This is I, and these are the input nodes, output nodes. How many are they? So this number is 6j, and this number is also 6j because of the 6j in concentrator. So from I, you first use the concentrator to go to I prime, which will be 4j vertices. Okay, so that's the concentrator business. And similarly here there is a concentrator. Okay, so I to I prime is is the concentrator we built in the lemma, and then O to O prime is also the same concentrator, but placed kind of in this reverse way, and I prime to O prime you basically recurse down and use a super concentrator. Okay, so this part is a super concentrator. Okay, so this is the almost the final construction. You use two concentrators or two copies of the same concentrator and one smaller super concentrator, and also have matchings. Finally, have a designated vertex. Okay, so these are actually matchings for I to O. So just I and O have the same number of vertices. You basically create a bijection and call that M. Okay, we'll call that a matching, the matching M. And the claim is that this graph is a super concentrator from I to O. Okay, it's a recursive construction. So design this. So this recurses from 6J to 4J, super concentrator. Okay, so this is the recursive construction, and in every step you need two copies of the concentrator. So why would this work? We'll analyze this next time.